In this lesson, we'll do another example involving limits. First, let's recall the definition of the limit that we've seen previously. We say that the limit as x goes to a of f of x is equal to L if we can make the values of f of x as close to L as we want by making x sufficiently close to a. So if the values of f of x are getting closer and closer to L as x gets closer and closer to a, we say that the limit as x goes to a of f of x is equal to L. Now in our first example, we were simply able to plug in our value of a to obtain the limit. Here, we want to find the limit as x goes to 0 of the expression 3 plus x quantity squared minus 9 all over x. So the first thing you should notice here is that this one is a little more complicated because if we tried to just plug in x equals 0, on the top we would get 3 plus 0, so 3, squared, which is 9, minus 9 is 0 over 0. And we know that we can't have a 0 in the denominator, so here, if we call our function f of x equals 3 plus x quantity squared minus 9 all over x, what we see is that f of 0 is undefined due to that x in our denominator. So we need to investigate our limit more carefully using some of the algebraic tools that we've just discussed earlier. First though, just like we did before, let's get a numeric sense of what's going on here. The limit as x goes to 0, so let's just plug in values of x that are close to 0. Again, I'm going to do both greater than 0 and less than 0. So again, go ahead and pause the video, take a calculator or computer, and figure out for these values of x, what are the corresponding values of f of x. When you're ready, come back and we'll put in our values. Okay, so for these values of x, we get the corresponding values of f of x. So it looks like the value of this function is getting closer and closer to the number 6 as x gets closer to 0. Let's see if we can observe that graphically as well. So here's a graph of the function f of x equals 3 plus x quantity squared minus 9 all over x. So of course this function is undefined at x equals 0, but we observe graphically that it does appear that the values of the function are getting closer to 6 as x gets closer to 0. Now let's see if we can figure out why this is the case analytically or algebraically. So let's go ahead and expand this expression in the numerator. So we're going to get 9 plus 6x plus x squared, and then minus 9, all of that over x. Now what we notice is that these 9's cancel, so we get simply 6x plus x squared all over x for our expression. And we see now that in the numerator we can factor out an x and we're left with 6 plus x. Now what we see is that our x's cancel, and of course when we cancel the x's, we're assuming that x is not equal to 0, but that's okay because we want the limit as x goes to 0. And if we remember from the definition of our limit that we're just making x close to 0, but not actually equal to 0. So going back to what we have now, we can cancel those x's. So we get limit x goes to 0 of 6 plus x over 1, or just limit x goes to 0 of 6 plus x. And now, just like with our x squared example, we can see that as x gets closer and closer to 0, 6 plus x is just getting closer and closer to 6. So our final answer here is that this limit is equal to 6. And again, we were able to see this numerically by looking at our table of values, graphically by looking at what happens to the graph for values of x close to 0, and ultimately analytically by using our algebraic techniques. In this case, we expanded our numerator and ultimately were able to cancel the x in the denominator.